Somewhere out there, hidden among the countless stars that dot the night sky, cosmic enigmas lurk. Secrets so strange they defy the very rules we thought bound the universe together. Picture this: a star cluster, a family of stars born from the same cosmic cradle, moving in ways that shouldn't be possible. Their orbits twist and turn as if tugged by invisible hands, their paths tracing patterns that leave even the most brilliant astronomers scratching their heads. These aren't just quirks of nature, they're full-blown rebellions against the laws of physics as we know them. And today, we're setting off on a journey to uncover 30 of these mind-bending anomalies, each one a puzzle piece in the grand mystery of galactic behavior. What makes these star clusters so baffling? Take gravity, for instance, the force that's supposed to keep everything in check. Yet here stars speed up when they should slow down or drift apart when they ought to stay bound together. Some clusters spin faster than their visible mass should allow, as if an unseen force is whispering to them from the shadows. Could it be dark matter weaving its unseen web, or something even more extraordinary, a flaw in our understanding of physics itself? These aren't just academic curiosities. They're clues that could rewrite our cosmic rulebook, revealing truths about the universe that we've only begun to dream of. So why should you care? Because these mysteries aren't locked away in some distant corner of space. They're part of the same cosmos we call home. Every unexplained wobble, every gravitational hiccup is a thread in the grand tapestry of the universe, waiting to be pulled. And as we explore these 30 anomalies together, you'll start to see the night sky differently, not as a static painting, but as a living, breathing enigma. By the time we're done, you might just find yourself questioning everything you thought you knew about the stars above. Ready to dive in? Let's unravel these celestial secrets, one astonishing discovery at a time. The first anomaly we encounter is one that shakes the very foundation of astrophysics, the missing mass problem. Picture a star cluster like a bustling city, where every streetlight represents a visible star. Now imagine the traffic flowing through those streets, the motions of stars as they orbit the cluster's center. According to the laws of gravity, the speed of that traffic should depend on how many streetlights or stars are present. But here's the twist. The stars are moving far faster than they should be, as if some unseen force is yanking them along. Telescopes scan the skies, searching for the hidden mass that must be causing this gravitational tug-of-war, yet they come up empty. Where is all this extra weight coming from? This isn't just a small accounting error, it's a cosmic discrepancy on an enormous scale. Some clusters behave as if they contain 10 times more mass than the stars we can actually see. So what's lurking in the shadows? One leading suspect is dark matter, the elusive substance thought to make up most of the universe's mass. It doesn't emit light, doesn't reflect it, and barely interacts with ordinary matter except through gravity. If dark matter is woven through these clusters like an invisible scaffold, that could explain the extra pull on the stars. But there's another, even wilder possibility. What if our understanding of gravity itself is incomplete? A few daring scientists have proposed tweaks to theory of general relativity, suggesting gravity might behave differently on cosmic scales. Imagine if the rules of the game changed slightly when dealing with enormous distances. Stars could then move in unexpected ways without needing any hidden matter at all. But before we rewrite the textbooks, we have to ask, why would gravity follow one set of rules in star clusters and another in galaxies? That's where the mystery deepens. Each new observation adds another layer to the puzzle, leaving us with more questions than answers. And here's what makes this anomaly so thrilling. It's not just about one cluster or one odd measurement. This missing mass problem pops up again and again in different corners of the universe, like a cosmic fingerprint left behind by something we don't yet understand. Whether it's dark matter, modified gravity, or something even stranger, solving this riddle could unlock secrets about the very fabric of reality. So as we move forward, keep this question in mind. What invisible hand is guiding these stars, And what else might it be shaping without us even knowing? Just when you thought star clusters couldn't get any stranger, along comes an anomaly that flips the script, literally. Imagine a bustling dance floor where every star moves in perfect harmony, swirling together in the same direction. Until suddenly, one star breaks formation, spinning backward like a rebel refusing to follow the rhythm. These are retrograde orbits, and they are one of the most baffling behaviors in stellar clusters. According to everything we know about star formation, these cosmic misfits shouldn't exist. Stars born from the same collapsing cloud of gas should share the same rotational direction, like siblings inheriting their parents' traits. So why do some stars defy this rule, spinning wildly out of sync with their neighbors? The answer might lie in chaos, violent, galaxy-shaking chaos. Picture a star cluster as a serene pond, its stars gliding smoothly in unison. Now imagine another cluster plowing through it like a boulder dropped into the water. The gravitational ripples from such a collision could send stars careening off course, some even flipped into reverse. These cosmic pileups might not be rare. In the crowded heart of galaxies, clusters frequently jostle and merge, leaving behind scars in the form of these backward-spinning stars. But here's the catch. Not all retrograde orbits can be explained by collisions alone. Some appear too pristine, too perfectly counter-rotating, as if they were born that way. That's where the theories get even wilder. Could these stars be interlopers, captured from passing galaxies or rogue clusters? Imagine a cosmic thief snatching a star from another system and flinging it into a new orbit, backward and out of place. Or perhaps the cluster itself harbors secrets, hidden substructures or gravitational quirks that nudge stars into rebellious paths over eons. There's even a tantalizing possibility that magnetic fields or dense pockets of dark matter could act like invisible hands, steering stars into these odd configurations. What makes retrograde orbits so thrilling isn't just their defiance of expectations, it's what they reveal about the universe's untamed nature. These backward-spinning stars are cosmic breadcrumbs, hinting at ancient collisions, galactic theft, or forces we haven't yet named. Every one of them is a challenge to our models, a reminder that the universe loves to throw curveballs. And as we peel back the layers of this mystery, we're not just solving a puzzle, we're witnessing the aftermath of celestial drama written in the stars themselves. Now we come to one of the most dramatic anomalies of all, stars that don't just misbehave, but outright flee their cosmic homes at breakneck speeds. These aren't your average wandering stars, these are ultra-fast escapers, stellar fugitives rocketing away from their clusters faster than physics should allow. Picture a firework bursting from a launcher, but instead of falling back to Earth, it vanishes into space at impossible velocity. That's the kind of energy we're talking about. Stars blasting off with such force that their cluster's gravity, which should act like an unbreakable tether, simply can't reel them back in. So where does this explosive energy come from? One leading theory points to cosmic catapults lurking in the heart of these clusters, black holes hidden and hungry. Imagine a tight-knit group of stars dancing around an invisible monster. If two stars swing too close to each other, their gravitational tango could fling one outward like a slingshot while the other spirals inward, doomed. This violent gravitational shuffle, known as the three-body interaction, might explain some of these runaway stars. But here's the twist. Not all escaping stars trace their paths back to the cluster's center, where black holes typically lurk. Some seem to get their kick from the edges, as if something else is at play. That's where tidal shocks enter the scene. Picture a star cluster drifting too close to a galaxy's dense core or plowing through a massive gas cloud. The gravitational turbulence from these encounters could act like a cosmic wave, lifting stars clean out of their orbits and hurling them into the void. But even this explanation doesn't always fit. Some ultra-fast escapers are solitary, streaking through space with no obvious trigger, no nearby galaxy or gas cloud to blame. And then there's the wild card. What if these stars were never truly part of the cluster to begin with? Could they be interstellar nomads, captured and then violently ejected by some unseen force? Or might they be the survivors of ancient collisions, fragments sent careening across the cosmos like shrapnel from a celestial explosion? The more we study these speed demons, the clearer it becomes. Their stories are as varied as they are mysterious. What makes ultra-fast escapers so captivating isn't just their speed. It's what they reveal about the chaos simmering beneath the seemingly orderly surface of star clusters. Every runaway star is a clue, a fingerprint of some violent or elusive event we've yet to fully understand. Whether it's hidden black holes, galactic turbulence, or something even stranger, these stellar escape artists challenge us to rethink the forces that shape the universe. And as we chase their trails across the cosmos, one thing's certain: the answers, when we find them, will be anything but ordinary. Deep in the hearts of some star clusters, there's a cosmic traffic jam defying all expectations. Imagine a stadium packed shoulder to shoulder with people, except instead of humans, it's stars, squeezed so tightly together that they should be constantly bumping into each other. Yet when astronomers peer into these overcrowded cores, they find something startling: far fewer collisions than the math predicts. It's as if an invisible traffic director is keeping these stars smoothly flowing, preventing cosmic fender benders against all odds. What makes this so puzzling? Take globular clusters, for instance, ancient, dense gatherings of stars where the core can contain thousands of stellar bodies crammed into a space just a few light-years across. At these densities, stars should be ricocheting like balls, leaving behind trails of shattered stellar debris. Computer simulations consistently forecast chaotic pileups, with stars merging or tearing each other apart in violent encounters. But when we look through telescopes, the reality is oddly serene. Where are the wreckage and the fireworks? One possibility is that we're missing a hidden stabilizing force. Picture a crowded subway platform where everyone instinctively adjusts their steps to avoid collisions. Could stars be doing something similar? Some researchers suggest subtle gravitational interactions, like gentle nudges between passing stars, might help maintain order over time. Others wonder if binary star systems, pairs locked in mutual orbits, act like shock absorbers, their coordinated motions preventing larger disruptions. Then there's the dark matter angle. If these clusters harbor unseen halos of dark matter, its gravitational influence might subtly rearrange stellar paths, creating pockets of stability amidst the chaos. But here's the catch: many of these clusters show no signs of harboring enough dark matter to explain the effect. It's like blaming a missing referee for the order in a game where no referee exists. Perhaps the most mind-bending theory involves the stars themselves. What if, over billions of years, the most unstable stars have already collided or been ejected, leaving behind a naturally calmer population? Like a forest that stopped burning because all the flammable trees are gone, these clusters might have self-regulated into their current, oddly peaceful state. But even this can't fully explain the eerie harmony we observe. The mystery of overcrowded cores isn't just about missing collisions. It's a window into how complex systems evolve under extreme conditions. Every well-behaved cluster challenges our assumptions, forcing us to ask: are we underestimating nature's ability to maintain balance, or overlooking something fundamental about how stars interact? As we continue to study these stellar metropolises, one thing becomes clear: their quiet centers speak volumes about the universe's hidden rules. Stretching across the cosmos like ghostly fingerprints, some star clusters leave behind trails so faint they're almost invisible until you look closer. These are tidal tails, ethereal rivers of stars that seem to have been pulled from their parent clusters by some unseen force. Picture a ball of yarn unraveling in slow motion, its threads stretching farther and farther into space. But here's the catch: many of these starry streams drift through regions of space where no obvious culprit, no massive galaxy or passing cluster exists to explain their formation. So what's yanking these stars into oblivion? The mystery deepens when you consider the math. For a cluster to stretch into such long, delicate tails, it needs to endure a gravitational tug-of-war powerful enough to overcome its own binding forces. Normally, this happens when a cluster ventures too close to a galaxy's gravitational field, much like how the moon's pull creates Earth's ocean tides. But some phantom tidal tails float in near-empty voids, light years away from any visible source of disruption. It's as if an invisible hand reached out, gripped the cluster, and let gravity do the rest. One possibility is that these clusters are remnants of ancient encounters, cosmic car crashes that happened so long ago, the galaxies responsible have since moved on, leaving no trace behind. Imagine two galaxies brushing past each other billions of years ago, their gravitational wakes stretching a cluster like taffy before they drifted apart. The stars, now stranded in these eerie streams, would bear silent witness to a drama long since vanished. But there's a twist. Some tidal tails are too pristine, too perfectly shaped to be relics of old collisions. Their symmetry suggests an ongoing influence, as if something unseen is still out there, gently shepherding the stars into these formations. Could dark matter be the architect? If dense clumps of it lurk in these seemingly empty regions, their gravity might sculpt the clusters in ways we can't yet detect. Or perhaps there's another, even stranger force at work, a flaw in our understanding of how gravity operates over vast distances. What makes these phantom tails so haunting isn't just their ghostly appearance, it's what they imply about the universe's hidden scaffolding. Every unexplained stream is a breadcrumb trail leading to questions we're only beginning to ask. Are we missing entire galaxies hiding in plain sight, cloaked by dust or distance? Or is the cosmos playing by rules we haven't quite deciphered? As we map these stellar rivers across the sky, one thing becomes clear: the universe is far from empty. It's teeming with invisible forces, quietly shaping the stars in ways we're just learning to see. Among the most puzzling mysteries in star clusters is the discovery of celestial odd couples, stars that shouldn't exist side by side. Imagine walking into a classroom where half the students are elderly professors and the other half are toddlers. That's the kind of age gap we're talking about here. Conventional wisdom says star clusters are born in a single, fiery burst of star formation, with all members sharing roughly the same birthday. But telescopes have revealed clusters where some stars are ancient relics, billions of years old, while others shine bright and young, as if they just ignited yesterday. How can these cosmic generations coexist in such tight quarters? One clue lies in the idea of stellar rejuvenation, a cosmic fountain of youth. Picture an older star, nearing the end of its life, drifting too close to a neighbor. In a dramatic gravitational embrace, the two might merge, their combined material reigniting nuclear fusion and creating what looks like a brand new star. This could explain why some clusters appear to host youthful outliers amidst an elderly population. But there's a catch. Not all age discrepancies can be chalked up to mergers. Some young stars sit isolated, with no signs of a violent past, as if they formed peacefully long after their cluster's initial birth. That's where the theory of extended star formation comes in. Instead of a single explosive event, some clusters might experience multiple waves of stellar births, like a city rebuilding itself over centuries. Dense pockets of gas lingering in the cluster's core could collapse under their own weight eons after the first stars lit up, creating fresh generations in a delayed cosmic encore. But why would gas stick around for so long without being blown away by stellar winds or radiation? Some researchers point to magnetic fields or dark matter's gravitational grip as possible culprits, trapping fuel for future star formation like a cosmic pantry. Then there's the wild card, interstellar adoption. Could these younger stars be cosmic orphans, captured from passing gas clouds or dwarf galaxies? Imagine a cluster drifting through a star-forming region, its gravity plucking newborn stars like apples from a tree. This might explain why some youthful interlopers seem chemically distinct from their older clustermates, as if they were born in a different corner of the galaxy. The implications of these age gaps ripple far beyond a single cluster. If stars can form in multiple epochs within these dense groups, it challenges our entire timeline of galactic evolution. Were some clusters once far more dynamic, with staggered births and complex histories? Or do they occasionally absorb fresh stars like celestial sponges, blurring the line between clusters and galaxies? Every mismatched age pair is a clue, a whisper from the universe that the story of star clusters is far richer and far stranger than we ever imagined. Among the ancient stars of these clusters, where most burn with the steady glow of old age, there are rebels that refuse to fade, stars that blaze with the vibrant blue hue of youth. These are the blue stragglers, cosmic anomalies that stand out like teenagers at a retirement home. By all accounts, they shouldn't exist. Star clusters age together, their members born from the same primordial gas cloud billions of years ago. So why do these youthful linger, shining brighter and hotter than their peers? The answer might be as dramatic as a stellar heist, or as strange as a cosmic resurrection. Picture two aging stars locked in a tight gravitational embrace. Over millions of years, one star begins siphoning material from its companion, stealing hydrogen fuel like a vampire draining lifeblood. This stolen gas reignites nuclear fusion in the thief's core, effectively hitting the reset button on it. The result? A star that looks freshly born, burning hot and blue while its donor withers away. This stellar vampirism could explain some blue stragglers, especially those found in binary systems with faint, depleted partners. But not all of these young-looking stars have obvious victims nearby. Some appear to be lone wolves, leaving astronomers scratching their heads. That's where another theory comes in: celestial collisions. Imagine two older stars, each plodding along in their golden years, suddenly smashing together in a violent merger. The combined mass and fresh fuel could trigger a second youth, creating a single hotter star from the wreckage. Computer simulations show such crashes are plausible in densely packed clusters, where stars frequently brush past one another. Yet even this explanation has gaps. Some blue stragglers are found in looser clusters where collisions should be rare, and others show chemical signatures that don't quite match what you'd expect from a straightforward merger. Perhaps the most puzzling cases are those that seem to have formed from scratch long after their cluster's birth. Could lingering pockets of gas have collapsed into new stars billions of years after the initial burst of star formation? Or might these stragglers be interstellar, captured from younger regions of the galaxy and adopted into the cluster? The more we study them, the clearer it becomes. Blue stragglers aren't a single phenomenon, but a cosmic detective story with multiple possible culprits. What makes these stars so fascinating isn't just their defiance of time. It's what they reveal about the dynamic, even chaotic nature of star clusters. They're proof that these systems aren't static museums of ancient stars, but living laboratories where gravity, chance, and physics conspire to rewrite the rules. Every blue straggler is a challenge to our understanding, a reminder that the universe never runs out of ways to surprise us. And as we piece together their secrets, we're not just solving a stellar mystery, we're uncovering the hidden life cycles of the cosmos itself. Among the countless star clusters dotting the cosmos, some behave like cosmic mayflies, here one moment and gone the next. These are the dwarf clusters, small gatherings of stars that vanish far quicker than our models predict, dissolving into the galactic void as if erased by an unseen hand. Picture a handful of sand tossed into the wind, grains scattering until nothing remains. That's the fate these clusters seem to meet, but here's the puzzle. Gravity should hold them together for billions of years. So why do so many fade away in just a fraction of that time? The mystery starts with their size. Dwarf clusters are the underdogs of the stellar world, containing anywhere from a few hundred to a few thousand stars, far fewer than the densely packed globular clusters that endure for eons. With less mass to bind them, they're more vulnerable to external forces. But even accounting for their modest size, simulations show they should stick around 10 times longer than they actually do. It's as if some invisible force is actively dismantling them, plucking stars away one by one. One prime suspect is the Milky Way itself. Imagine a cluster orbiting our galaxy, passing through dense patches of gas or the gravitational wake of spiral arms. These encounters could act like cosmic sandpaper, gradually stripping stars away through a process called tidal disruption. Yet when astronomers map the trajectories of vanishing dwarfs, not all of them venture close enough to the galaxy's disruptive regions to explain their rapid demise. Some disintegrate in relatively quiet corners of space, far from any obvious threat. That's where dark matter enters the scene. If these clusters are embedded in diffuse halos of dark matter, invisible scaffolding that helps bind them, their sudden disappearance makes even less sense. The extra gravitational glue should make them more resilient, not less. Unless, of course, the dark matter itself is being torn away by something we can't see. Could unseen structures, filaments of dark matter or rogue black holes, be lurking along these clusters' paths, gutting them from the inside out? Then there's the wild card, internal rebellion. Some dwarf clusters might be born unstable, their stars so loosely bound that even minor nudges from passing gas clouds or supernova shocks could send them drifting apart. Think of a house of cards built on a wobbly table. The slightest tremor brings the whole structure down. But if that's the case, why do some small clusters, against all odds, manage to survive for ages while they crumble away? The case of the vanishing dwarfs isn't just about missing stars. It's a window into the delicate balance of forces shaping our galaxy. Every cluster that disappears too soon forces us to ask, are we underestimating the chaos of interstellar space, or overlooking something fundamental about how gravity works on the smallest scales? These fleeting clusters might be cosmic canaries in the coal mine, hinting at invisible dangers or hidden laws we've yet to uncover. And as we race to solve their disappearance, one thing's certain. The universe has a way of reminding us how much we still don't know. In the intricate dance of star clusters, binary systems should be the epitome of predictability. Two stars locked in a graceful orbital waltz, governed by the unbreakable laws of gravity. But the universe, as always, loves to subvert expectations. Some of these stellar pairs whirl around each other at distances so vast they defy logic, while others cling so tightly they nearly touch, spinning faster than physics should allow. These aren't just quirks, they're full-blown rebellions against our models of how binary stars should behave. And behind each anomaly lies a story of near misses, violent encounters, or perhaps unseen players pulling the strings from the shadows. Take the case of wide binaries, pairs separated by distances so large they shouldn't survive the gravitational turmoil of a dense cluster. Imagine two dancers trying to maintain a partnership while being shoved apart by a crowd. Eventually, they'd lose each other entirely. Yet these stars persist, bound together despite the chaos. One theory suggests they're survivors of ancient collisions, their orbits stretched like taffy during close encounters with other stars or black holes. Another idea. They might not have formed together at all. Instead, they could be strangers captured by the cluster's gravity and forced into an uneasy alliance, like two solo artists suddenly paired for a duet they never rehearsed. Then there are the ultra-close binaries, stars orbiting so near they exchange material in a cosmic game of tug-of-war. These pairs should spiral inward and merge within millions of years, yet some endure for billions, seemingly frozen in time. What's keeping them apart? Hidden forces might be at work. Perhaps a third star, invisible to our telescopes, orbits just far enough to stabilize the system like a gravitational mediator. Or maybe magnetic fields act as brakes, preventing the stars from collapsing into one another. The most baffling cases are those where the stars spin in perfect sync, their rotations locked to their orbits as if choreographed by an unseen hand. But the real enigma lies in the binaries that shouldn't exist at all, pairs with mismatched sizes, ages, or chemical compositions. Picture a heavyweight boxer teamed with a ballet dancer. Their partnership makes no sense unless something extraordinary happened in their past. Some might be the product of stellar theft, where one star ripped a companion away from another pair during a close encounter. Others could be Frankenstein's monsters, stitched together from the remnants of long-dead stars. And a few might even be their light blending in ways that trick us into seeing a binary where there's only one star with a peculiar atmosphere. What makes these odd couples so compelling isn't just their defiance of rules, it's what they reveal about the hidden dramas playing out in star clusters. Every misbehaving binary is a clue, a snapshot of the chaos and creativity that shape the cosmos. Whether it's unseen companions, ancient collisions, or forces we've yet to discover, these systems remind us that the universe doesn't follow scripts, it improvises. And as we unravel their secrets, we're not just solving puzzles, we're witnessing the unscripted, ever-surprising ballet of the stars. At the heart of some star clusters, a cosmic tug-of-war rages, one where gravity should have already declared victory. Picture a skyscraper swaying in a hurricane, its steel frame groaning under the strain, yet somehow standing tall century after century. That's the essence of the core collapse conundrum. Clusters so dense, so tightly packed, their cores should have crumpled inward eons ago under their own weight. But when astronomers peer into these stellar beehives, they find not chaos, but an eerie equilibrium. Stars buzz around the center like bees around a hive, never quite collapsing into the catastrophic crunch the math insists is inevitable. So what's holding them up? One theory points to stellar speedsters, rogue stars whipping through the core at breakneck velocities. Imagine a dozen pinballs ricocheting through a crowded room, their kinetic energy keeping the space from collapsing inward. In clusters, these high-speed stars might act like cosmic shock absorbers, their motion generating enough outward pressure to counterbalance gravity's relentless pull. But here's the catch. Not all clusters on the brink of collapse host enough of these stellar speed demons to explain their stability. Some teeter on the edge, their cores seemingly suspended by invisible threads. That's where dark matter re-enters the stage. If these clusters are embedded in diffuse halos of unseen mass, their gravitational scaffolding might redistribute energy from the outskirts inward, like a hidden hand propping up a wobbling tower. Yet observations of some clusters reveal little trace of dark matter where it should be most concentrated, right at the core. It's as if the universe is taunting us with a magic trick, the starry equivalent of a table floating midair with no strings attached. Perhaps the most radical idea is that we're missing a fundamental piece of physics. Could gravity behave differently in these extreme environments? Modified Newtonian dynamics, or MOND, suggests that on cosmic scales, gravity's strength might taper off less sharply than its equations predict. In a dense cluster core, this subtle tweak could mean the difference between a slow-motion collapse and a lasting stalemate. But even this can't fully explain why some clusters hover indefinitely at the brink, while others, seemingly identical, plunge into collapse without warning. Then there's the wild card, black holes. Not the supermassive monsters anchoring galaxies, but smaller, intermediate-mass black holes lurking unseen in cluster cores. These hidden heavyweights could stir the stellar pot, their gravity slinging stars outward like a spoon swirling cream into coffee, preventing a catastrophic pileup. A few clusters show tantalizing hints of such invisible anchors, stars orbiting empty patches of space at dizzying speeds. But without direct evidence, the question remains, are we seeing the work of black holes or something even stranger? The core collapse conundrum isn't just about stars defying gravity. It's a window into the universe's delicate balancing acts. Every stable cluster whispers secrets about the forces, seen and unseen, that shape cosmic structures. Whether it's dark matter's subtle grip, black holes stirring chaos, or physics begging for revision, one thing's clear: the answers won't just solve a stellar mystery. They'll redefine how we understand the invisible architecture holding the cosmos together. In the bustling stellar cities of star clusters, where stars jostle shoulder to shoulder in dizzying numbers, there's an eerie phenomenon that defies logic: vast, starless voids where nothing seems to gather. These aren't the expected gaps between orbits or the quiet outskirts of a cluster. These are mysterious dead zones, regions where stars actively avoid congregating, as if some invisible barrier were keeping them out. Picture a crowded dance floor with a perfect circle of empty space at its center. No matter how packed the room gets, no one dares step into that spot. That's the kind of cosmic anomaly we're dealing with here. What makes these voids so baffling is that they exist where gravity insists they shouldn't. In a cluster's dense core, every star's pull should draw others inward, filling gaps over time like water leveling in a bowl. Yet these hollows persist, sometimes spanning light years, untouched by the gravitational tides around them. One leading theory suggests they're scars from ancient violence, cosmic bullet holes left behind when black holes or massive stars were ejected from the cluster in a cataclysmic event. Imagine a game of pinball where the heaviest ball suddenly rockets off the table, leaving behind a void where other balls now refuse to roll. The gravitational aftershocks of such an exit could carve out a lasting emptiness. But there's a twist: not all voids align with this collision narrative. Some sit like symmetrical bubbles in the cluster's heart, too perfectly round to be random wreckage. That's where stranger ideas emerge. Could these zones harbor repulsive forces we've yet to identify? Some theorists speculate about exotic physics, perhaps dark energy, which drives the universe's expansion, operates on microscopic scales here, pushing stars apart in localized pockets. Others wonder if extreme magnetic fields, generated by long-dead stars, might act like cosmic force fields, shepherding stars away like sheep avoiding an electrified fence. Then there's the wildest possibility of all, that these voids are observational illusions. What if they're not empty at all, but filled with something our telescopes can't see? Cold, dark objects like rogue planets or black holes could lurk there, their mass warping space just enough to deflect incoming stars without emitting detectable light. It's like walking into a room and feeling an inexplicable chill. No visible source, but the air itself seems to recoil. The more we study these ghostly gaps, the clearer it becomes. They're not accidents. They're clues. Whether they're footprints of ancient chaos, shadows of unseen forces, or something beyond our current imagination, these voids challenge the very way we map the universe's crowded neighborhoods. And with every new observation, we're forced to ask, what else is hiding in plain sight, quietly reshaping the cosmos in ways we're only beginning to sense? Gravity is supposed to be the universe's great equalizer, a force so predictable we use it as a cosmic measuring tape. But star clusters have a way of bending the rules, even when it comes to light itself. Hear how it works. When a massive cluster sits between us and a distant galaxy, its gravity should warp the fabric of spacetime, magnifying and distorting the galaxy's light like a funhouse mirror. The stronger the cluster's gravity, the more dramatic the distortion. Simple, right? Except when we compare the lensing effect to the cluster's visible mass, the math never adds up. The light bends too much, as if the cluster contains far more weight than the stars we can see. This isn't just a minor accounting error. Some clusters act like cosmic con artists, their gravitational lenses suggesting they're 10 times heavier than their starlight reveals. Imagine stepping on a scale that claims you weigh 1,000 pounds, but when you look down, your body hasn't changed. That's the kind of discrepancy astronomers face. So what's really doing the heavy lifting? Dark matter is the usual suspect, its invisible bulk amplifying gravity's grip without emitting a single photon. But here's the twist. The lensing patterns don't always match where dark matter should be. Some clusters distort light in ways that suggest their hidden mass isn't smoothly distributed, as models predict, but clumped in strange, asymmetrical ways. That's where things get even weirder. A few of these cosmic lenses appear to have hotspots, pockets of space where the warping is so extreme, it's as if invisible anvils are piled in one corner of the cluster. No known form of dark matter behaves like this. Could there be entire structures of unseen matter, tangled like cosmic spiderwebs, bending light in unpredictable ways? Or might we be glimpsing something even more exotic? Primordial black holes, forged in the early universe and lurking unseen, or hidden dimensions warping gravity itself. The most tantalizing possibility, we're seeing gravity play by different rules. Some theorists argue that if we tweak equations just slightly, allowing gravity to strengthen under certain conditions, these mismatches might make sense. But before we rewrite the textbooks, we have to ask, why would gravity suddenly shift its behavior inside star clusters but nowhere else? What makes these lensing anomalies so thrilling isn't just the mystery, it's the method. Every distorted galaxy is a flashlight illuminating the cluster's hidden skeleton. With each new observation, we're not just mapping darkness, we're decoding the universe's silent language of gravity. And the more we learn, the clearer it becomes. The cosmos is still keeping secrets, written in the warped light of distant stars. In the bustling stellar neighborhoods of star clusters, where most stars share the same chemical fingerprints like siblings from the same parent, there are puzzling outliers, cosmic orphans with compositions that don't match the family album. These interstellar strays, rich in elements their clustermates lack or missing key ingredients everyone else has, stick out like strangers at a family reunion. Their very presence raises a tantalizing question. How did stars born in another corner of the galaxy end up here, locked in the gravitational embrace of a cluster they weren't born into? One clue lies in the chaotic ballet of galactic collisions. Picture a star cluster drifting through the Milky Way, its gravity snatching passing stars like a cosmic net. Dwarf galaxies or smaller clusters, rich in unique stellar chemistry, might have brushed too close, leaving behind a few of their members as celestial souvenirs. Over time, the captured stars would blend into their new home, their unusual compositions the only evidence of their extraterrestrial origins. But here's the catch. Some orphan stars show chemical signatures so distinct they couldn't have come from any known neighbor. Their birthplaces must lie farther away, perhaps in long-vanished galaxies swallowed by the Milky Way eons ago, their stars scattered like breadcrumbs across the cosmos. Then there's the possibility of stellar adoption by proxy. Imagine a massive gas cloud, pregnant with newborn stars, drifting into a cluster's orbit. As the cloud gets torn apart by tidal forces, the fledgling stars inside could be deposited into the cluster like foundlings left on a doorstep. These stars would carry the chemical imprint of their original cloud, a mix of elements different from the cluster's native population. But even this explanation falters when faced with orphans that are billions of years older than their adopted siblings, ruling out recent arrivals. The plot thickens when you consider the rogue stars, loners ejected from their birth clusters by violent encounters, only to be captured by another. A close brush with a black hole or a gravitational slingshot from a dense binary system could send a star careening across the galaxy until it's ensnared by a new cluster's gravity. These cosmic refugees would bear the scars of their journey, their atmospheres potentially altered by eons of interstellar travel. Yet some orphans show no signs of such trauma, their chemistry pristine, as if gently placed into their new home by an unseen hand. The most mind-bending theory: some of these stars might not be orphans at all. Instead, they could be the products of exotic stellar mergers or collisions, their unusual compositions forged in the furnaces of violent encounters. Picture two stars with different chemical profiles smashing together, their remnants blending into a hybrid that defies classification. If such events happened early in a cluster's life, the resulting stars could masquerade as outsiders, their true origins lost to time. What makes these interstellar orphans so compelling isn't just their mysterious pasts. It's what they reveal about the dynamic, interconnected nature of our galaxy. Every misfit star is a testament to the universe's messy, improvisational history, where gravity plays the role of both architect and thief. Whether they're captured wanderers, adopted newborns, or reshaped survivors, their stories challenge the idea that star clusters are closed family units. Instead, they're cosmic melting pots, their populations shaped by encounters we're only beginning to piece together. And as we trace their chemical fingerprints back to their sources, we're not just solving a stellar mystery, we're mapping the Milky Way's hidden genealogy, one orphan star at a time, among the orderly ranks of stars in a cluster, where most spin at predictable speeds like synchronized dancers. There are wild outliers, stars whirling so fast they seem ready to fly apart. These rapid rotators defy all expectations, spinning at velocities that should have been impossible given their age and environment. Picture a seasoned ballet dancer suddenly breaking into a frenetic pirouette, their movements so intense they threaten to tear their own costume. That's the kind of cosmic defiance we're dealing with here. The mystery begins with angular momentum, the same principle that keeps a figure skater spinning faster as they pull their arms in. Stars are born from collapsing clouds of gas, inheriting their initial spin from this primordial rotation. Over time, stellar winds and magnetic braking should slow them down, like a top gradually losing steam on a table. Yet in clusters, some stars defy this slowdown, maintaining breakneck speeds billions of years after their birth. What's keeping them wound so tight? One possibility is celestial theft, stellar vampirism on a grand scale. Imagine a star locked in a tight orbit with a neighbor, siphoning off its outer layers like a cosmic whirlpool. The stolen material doesn't just feed the thief, it transfers angular momentum, spinning the predator star faster like a merry-go-round pushed by invisible hands. Binary systems where this occurs, known as spun-up stars, do exist, but they can't account for all the rapid rotators. Some of these speed demons are lone wolves, with no nearby companion to blame for their hyperactivity. That's where collisions come into play. In the crowded core of a cluster, stars brush past each other far more often than in the galactic suburbs. A close encounter, or even a direct hit, could deliver a gravitational kick, sending a star into a dizzying spin. Picture two ice skaters colliding mid-rink, their limbs tangling in a way that sends one spinning wildly out of control. Yet even this explanation has limits. Some fast spinners reside in loose clusters where such violent encounters should be rare, their isolation making their frenzied rotation even more baffling. Then there's the dark horse candidate, magnetic fields. Stars are laced with powerful magnetic forces, their invisible lines threading through their atmospheres like cosmic puppet strings. Under the right conditions, these fields might act like internal springs, storing rotational energy that gets unleashed in sudden bursts. Think of a twisted rubber band finally snapping back, releasing all its pent-up energy at once. If clusters harbor unique magnetic environments, perhaps amplified by unseen dark matter or turbulent gas, they could be spinning up stars like celestial tops. But the most tantalizing clue lies in the stars themselves. Some rapid rotators show unusual chemical signatures, their surfaces peppered with elements that suggest violent pasts. Could they be the survivors of ancient mergers, their cores scrambled by collisions long ago, leaving behind engines that never stopped revving? Or might they have ingested smaller, fast-spinning companions, absorbing not just their mass but their momentum? Every new observation adds another layer to the puzzle, revealing a universe where stars don't always play by the rules. What makes these fast spinners so captivating isn't just their speed, it's the sheer audacity of their existence. They're cosmic, challenging our understanding of how stars live, evolve, and interact. Whether they're thieves, survivors, or products of hidden forces, their whirlwind lives remind us that even in the vast, ordered structures of star clusters, chaos still finds a way to dance. Among the many mysteries lurking in star clusters, few are as eerie as the X-ray ghosts, faint, glowing halos of high-energy light with no visible source. Imagine walking through a foggy graveyard at night, spotting flickering lanterns in the distance, only to find no one holding them when you get closer. That's the kind of spine-tingling puzzle astronomers face when they point X-ray telescopes at certain clusters and detect diffuse, luminous patches where nothing should be shining. These emissions don't match the usual suspects. No neutron stars, no supernova remnants, not even the telltale heat of colliding gas. So what's lighting up these cosmic specters? The leading theory involves black holes, but not the kind you'd expect. Most clusters are too old to host the brilliant, feeding supermassive black holes seen in active galaxies. Instead, these X-ray ghosts might be the work of smaller, intermediate-mass black holes, lurking unseen in the cluster's depths. Picture a phantom predator, invisible but for the ripples it leaves in the surrounding stars. As these black holes drift through the cluster, their gravity could strip material from passing stars or gas clouds, creating a faint, smeared-out glow of X-rays as the stolen matter spirals into oblivion. Yet when astronomers scour these regions with optical telescopes, they often find no trace of the disruptors themselves, just the ghostly afterglow of their meals. Then there's the dark matter angle. If certain exotic particles, like hypothetical axions or sterile neutrinos, were to decay or collide within the cluster, they might release X-rays as a byproduct. These particles, unlike black holes, would leave no gravitational fingerprints, just an ethereal radiance hanging in space like cosmic fog. Some researchers even speculate that we're seeing the faint echoes of long-dead stars, their remnants having evaporated into clouds of ultra-hot plasma that still pulse with residual energy billions of years later. But the real twist: some of these X-ray ghosts appear to move. Over years of observations, their glow subtly shifts, as if whatever's causing it is drifting through the cluster like an unseen wanderer. Could these be the trails of rogue black holes, ejected from galactic centers and now haunting the outskirts? Or might they be evidence of something even stranger, cosmic strings, topological defects in spacetime itself, radiating energy as they vibrate across the universe? What makes these phantom emissions so compelling isn't just their mystery. It's what they imply about the hidden lives of star clusters. Every unexplained glow is a breadcrumb trail leading to forces we've yet to name, whether they're lost black holes, exotic physics, or entirely new celestial phenomena. And as our telescopes grow sharper, these X-ray ghosts may finally step into the light, revealing secrets that could rewrite our understanding of the universe's darkest corners. Star clusters are supposed to be cosmic families, groups of stars moving together through space like a school of fish in sync. But some clusters hide members that can't seem to follow the rhythm. These rogue stars exhibit slight differences, their light stretched just enough to reveal they're moving at speeds that defy the cluster's gravitational embrace. It's as if you spotted one fish suddenly darting upstream while the rest glide downstream, an anomaly that begs the question: are these stars truly part of the group, or just passing strangers caught in a fleeting cosmic handshake? The stretching of light toward the red end of the spectrum typically tells us how fast an object is moving away from us. In a bound cluster, stars should share similar, their motions harmonized by gravity. But when certain stars stand out with slightly shifted light, it suggests they're either racing toward escape velocity or never belonged in the first place. The mystery deepens when these outliers don't fit the profile of typical interlopers. Stars flung from other systems usually arrive with more dramatic velocity differences. These subtle deviations hint at something stranger, Perhaps the cluster itself is playing tricks on us. One explanation points to gravitational slingshots, close encounters between stars that fling one outward like a stone from a catapult. Imagine two stars swinging past each other in the cluster's crowded core, their dance ending with one star ejected at high speed while the other sinks deeper into the gravitational well. The ejected star might linger at the cluster's edge, it's betraying its near-escape velocity, but not all rebels trace back to such violent origins. Some drift along at odd angles, their paths suggesting they're just passing through, temporary guests in a system they'll soon leave behind. Then there's the dark matter factor. If clusters contain unseen pockets of mass, their uneven gravity could nudge stars into unexpected orbits, creating variations that mimic the presence of interlopers. Think of it as a hidden current in a river, tugging a few fish off course while the rest swim straight. But without direct evidence of dark matter's distribution, this remains a tantalizing what if. The most puzzling cases are stars that show chemical fingerprints matching their cluster's unique makeup, proof they were born there, yet move like outsiders. Could these be the survivors of ancient mergers, their orbits scrambled when another cluster collided with their home? Or might they be evidence of a cluster's slow disintegration, with gravity's grip weakening over eons, allowing stars to peel away one by one? Every outlier is a cosmic detective story. Whether they're escape artists, interstellar nomads, or signs of hidden forces at work, their unexpected motions remind us that even the most tightly bound stellar families have their share of rebels, and their secrets are written in the light they leave behind. Star clusters are supposed to be chemical time capsules, stellar siblings forged from the same primordial gas cloud, their atmospheres carrying matching metallic fingerprints like DNA passed down from shared ancestors. But scattered among these cosmic families are puzzling black sheep, stars glittering with far more or far less metal than their clustermates, as if they were strangers at a reunion. These metallicity outliers don't just break the rules, they shred the textbook on how star clusters form and evolve. If all stars in a cluster are born from the same well-mixed soup of gas, how can some end up with completely different recipes? Take globular clusters, ancient gatherings of stars thought to be among the examples of single-generation formation. Their members should be nearly identical in composition, like bottles from the same vintage. Yet spectroscopic studies reveal shocking exceptions. Stars with iron abundances 10 times higher than their neighbors, or bizarrely low levels of elements like oxygen and magnesium. It's as if someone slipped a spoonful of salt into a single glass from a perfectly uniform pitcher of water. The first instinct might be to blame contamination. Perhaps these oddballs were captured from passing gas clouds or smaller clusters. But many metallic outliers share the same precise orbits and ages as their siblings, proving they've been part of the family since birth. That's where the theories get inventive. One possibility involves pollution from the cluster's earliest days. Imagine the first generation of massive stars, living fast and dying young in spectacular supernovas. Their explosive deaths would seed the surrounding gas with fresh metals. But what if that enriched material wasn't evenly distributed? Dense pockets might have lingered like cosmic puddles, contaminating only select stars forming later. Picture a baker adding chocolate chips to just half the batter. The resulting cookies would share the same base ingredients, but carry wildly different extras. Then there's the wild card of stellar cannibalism. Some metal-rich outliers might be the products of ancient mergers, where two or more stars collided and fused their atmospheres into a single, chemically scrambled hybrid. In a crowded cluster core, such smash-ups wouldn't be rare, and the resulting stars would carry a mishmash of elements unlike anything formed from pristine gas. Others could be vampiric thieves, Having siphoned metal-enriched material from companion stars over billions of years, their surfaces now gleaming with stolen wealth. But the most tantalizing explanation challenges the very notion of uniform formation. Could some clusters have experienced multiple waves of star birth, with later generations forming from gas subtly altered by earlier stellar activity? Recent simulations suggest that even in supposedly single-age clusters, pockets of gas might remain cool and dense enough to collapse into stars millions of years after the main burst, enough time for chemistry to shift. It's like realizing your identical twins are actually fraternal, with one subtly altered by a hidden environmental factor. What makes these Metallicity rebels so revolutionary isn't just their existence. It's what they reveal about the messy, dynamic nature of star formation. Every outlier forces us to reconsider how elements mix and settle in the cosmic nursery, and whether our clean models of cluster evolution have been missing the chaos all along. They're not just anomalies, they're celestial archaeologists, their unexpected compositions hinting at forgotten collisions, hidden star-making episodes, or physics we've yet to name. And as we decode their metallic messages, we're not just solving a puzzle, we're rewriting the recipe book of the universe itself. Some regions of space have all the gravitational muscle of a star cluster, pulling on nearby stars, bending light, even shaping the motions of galaxies. Yet when astronomers point their telescopes at them, they see nothing. No glittering swarms of stars, no glowing gas clouds, just eerie stretches of darkness that somehow weigh as much as thousands of suns. These are the dark cluster candidates, cosmic ghosts that challenge everything we thought we knew about how stellar families form and evolve. The first clue to their existence came from gravity's fingerprints. When stars or galaxies move in ways that can't be explained by visible matter alone, astronomers map the unseen mass tugging at them, like sensing a hiding child by the depressions in a mattress. Some of these gravitational hotspots align perfectly with the expected locations of star clusters, except there's no starlight to be found. It's as if someone erased the stars but left their gravity behind. One explanation is that these are failed clusters, stellar nurseries that never quite ignited. Picture a collapsing cloud of gas, dense enough to birth stars but starved of some critical ingredient. Perhaps the gas was too cold, too turbulent, or stripped away by galactic tides before fusion could spark. The result, a shadowy pocket of dark matter and stray gas, its gravitational potential never realized. These cosmic stillbirths would linger like abandoned construction sites, their blueprints intact but their towers never built. Then there's the dark matter angle. Could these invisible anomalies be pure clumps of the universe's most elusive substance? Simulations suggest dark matter should form dense knots, especially in the turbulent wakes of galaxy collisions. If one of these knots gathered enough ordinary gas to mimic a cluster's gravity without ever forming stars, it would match the observations perfectly. But here's the catch. Dark matter alone shouldn't bend light as sharply as some dark clusters do. There must be something extra, perhaps rogue planets, black holes, or cold, dead stars, adding unseen weight. The most unsettling possibility. These aren't clusters at all, but something entirely new. Imagine a cosmic hall of mirrors where warped spacetime creates the illusion of mass where none exists. Or consider primordial black holes forged in the universe's first seconds, lurking in packs like wolves in the dark. Some theorists even speculate about exotic objects, cue balls, or other hypothetical creatures of particle physics that could masquerade as missing clusters. What makes these dark candidates so compelling isn't just their mystery, it's what they imply about the universe's hidden anatomy. Every blank patch on the map forces us to ask, are we seeing the ruins of a cluster that never was, the footprint of something we've yet to name, or a flaw in our cosmic census? Until we peer deeper into the darkness, one thing's certain: the universe loves to hide its greatest secrets in plain sight. 19th Anomaly, the The runaway clusters, entire small clusters, sometimes move at speeds that should eject them from their host galaxies, yet they remain bound. What launched these clusters so violently without breaking them apart? The dynamics defy expectations. Picture a comet streaking through the solar system, so fast it should escape the sun's gravity, yet somehow it stays trapped in orbit. Now scale that up to an entire star cluster, a family of thousands of stars hurtling through space at velocities that ought to fling them into the cosmic void. These runaway clusters aren't just fast, they're moving with enough kinetic energy to break free from their host galaxies entirely. Yet when astronomers track their paths, they find these stellar fugitives still tethered, as if some invisible leash keeps them from fleeing. How can something so massive move so recklessly without tearing itself apart or vanishing into intergalactic space? One clue lies in the violence of galactic cores. Imagine a cluster drifting too close to the supermassive black hole at a galaxy's heart. The gravitational slingshot from such an encounter could launch it outward at blistering speeds, like a stone flung from a catapult. But here's the twist. The same tidal forces that accelerate the cluster should also shred it, stripping stars away like leaves in a hurricane. Yet many runaway clusters emerge intact, their structures surprisingly cohesive. This suggests the launch mechanism wasn't just powerful, it was precise, delivering a kick strong enough to send the cluster racing without ripping it to pieces. Then there's the dark matter factor. If these clusters are embedded in dense halos of invisible mass, their extra gravitational glue might help them withstand the ejection process. Think of it like a net holding a bundle of marbles together. Even if you throw it hard, the net keeps the marbles from scattering. But not all runaway clusters show signs of harboring enough dark matter to explain their resilience. Some appear to be held together by sheer luck or some other hidden force, defying the odds with no obvious safety net. The most baffling cases are those where the cluster's speed doesn't trace back to any visible catastrophe. No nearby black hole, no signs of a past galactic collision, just a cluster hurtling through space with no apparent. Could these have been accelerated by something we can't see, like a close encounter with a massive but invisible dark matter? Or might they be relics of ancient galactic mergers, their motion imprinted by gravitational waves from long-vanished collisions? What makes these runaway clusters so mesmerizing isn't just their speed, it's the sheer improbability of their survival. They're cosmic, escaping certain doom without losing a single star. Whether they're products of perfect gravitational timing, shielded by dark matter, or witnesses to forces we've yet to name, their existence forces us to rethink how galaxies and their stellar families interact. Every one of them is a reminder that the universe doesn't just play by the rules, it sometimes rewrites them mid-game. Among the steady glow of stars in a cluster, where most shine with the reliability of distant lighthouses, there are unpredictable giants, massive stars that flicker like candles in the wind, their brightness surging and fading without rhyme or reason. These aren't your typical variable stars, whose pulses follow rhythmic beats like a cosmic metronome. These are the flickering giants, stellar anomalies that defy classification, dimming and flaring in chaotic bursts that leave astronomers scrambling for explanations. Imagine a stage where every performer moves in perfect sync, except for one, who dances to a rhythm only they can hear. That's the kind of cosmic rebellion we're witnessing here. What makes these flickers so baffling is their sheer unpredictability. Most variable stars operate on strict schedules, pulsating with the precision of a clock or dimming regularly as orbiting companions eclipse them. But these erratic giants flare up without warning, sometimes doubling in brightness overnight before fading just as suddenly. No known stellar process, no pulsation, no eclipse, no surface eruption can account for such wild swings. One moment they're steady beacons, the next they're sputtering like faulty. The leading theory points to hidden companions, unseen stars, or black holes stirring up chaos. Picture a massive star with a mischievous neighbor, its gravity warping the giant's outer layers, triggering violent tides of gas that erupt unpredictably. Yet when astronomers search for these hypothetical partners, many flickering giants appear to be alone, their solitude deepening the mystery. Then there's the possibility of internal upheaval. Stars this massive live fast and furiously, their cores churning like tempests. Could unstable fusion reactions deep within them be sending shockwaves to the surface, blasting away chunks of atmosphere in fits and starts? It's like a pot of water boiling over, except instead of steam, its entire stellar flares bursting forth. Some flickering giants even spew bizarre chemical signatures alongside their light shows, their spectra laced with elements that suggest violent mixing between core and surface layers. But why would this happen only to a select few stars in a cluster, while others of similar size burn steadily? The wildest hypothesis: we're witnessing entirely new stellar physics. Perhaps magnetic fields, twisted into knots by the star's rapid rotation, are snapping like rubber bands, releasing energy in erratic bursts. Or maybe dark matter, if it's concentrated in these clusters, could be interacting with the star's interior in ways we've never imagined, sparking strange eruptions. There's even a fringe idea that these flickers are signs of advanced stellar evolution, a previously unseen phase where massive stars begin to unravel in fits of instability before their final collapse. What makes these flickering giants so mesmerizing isn't just their defiance of expectations, it's the sheer audacity of their existence. Every unpredictable flare is a challenge, a dare from the universe to look closer, think deeper, and admit how much we still don't understand. Whether they're hiding companions, suffering internal breakdowns, or heralding new physics, one thing's clear: the cosmos still has surprises up its sleeve, and these stars are just the beginning. Star clusters are cosmic graveyards, ancient gatherings where generations of stars have lived, died, and left behind their remnants. Logic says these stellar corpses should litter the scene: dense neutron stars and black holes, the silent tombstones of massive stars long gone. Yet when astronomers peer into old clusters, they find a startling shortage of these expected remains. It's like excavating a battlefield and finding weapons, armor, and flags, but curiously few skeletons. So where did all the dead stars go? The math is straightforward. A typical globular cluster, billions of years old, should host hundreds of neutron stars and dozens of black holes, the relics of its most massive original members. But observations reveal only a fraction of that number. Some clusters appear almost sterile, their expected stellar cadavers conspicuously absent. One explanation points to gravitational pinball, chaotic interactions in the cluster's crowded core. Picture a neutron star, barely the size of a city but weighing more than the sun, zipping through a dense stellar neighborhood. Close encounters with other stars or black holes could slingshot it outward like a cosmic bullet, ejecting it entirely from the cluster. Over eons, this gravitational shuffle might purge the cluster of its dead, leaving behind only the lucky few that avoided violent collisions. But here's the catch: not all missing remnants can be blamed on ejections. Some clusters have cores so dense and stable that even the most violent interactions shouldn't have cleared them out completely. That's where the formation quirks theory comes in. Perhaps these clusters never formed as many massive stars as we assumed. Maybe their initial stellar populations skewed oddly lightweight, leaving fewer progenitors to create neutron stars and black holes in the first place. Imagine a town where, by sheer chance, very few people lived past 40. The local cemetery would naturally hold fewer graves. Then there's the dark matter wrinkle. If old clusters are embedded in diffuse halos of invisible mass, their gravitational dynamics could differ radically from our models. Dark matter's extra pull might stabilize orbits, reducing the chances of stellar ejections, yet somehow the dead stars are still missing. This paradox suggests something even stranger. Maybe black holes, once formed, don't stay put. Some simulations show they sink to the cluster's core, merging into a single, invisible monster that lurks undetected. Others propose they form tight binaries, their gravitational waves spiraling them out of the cluster entirely over cosmic time. The most tantalizing possibility: we're not looking hard enough. Neutron stars, especially those not actively feeding, are notoriously faint, dark cinders drifting unseen until they happen to flicker as pulsars or collide with a neighbor. Black holes, unless they're devouring gas, are even stealthier. Could these remnants be hiding in plain sight, camouflaged by the cluster's glow? Or might they have migrated to the cluster's outer edges, avoiding detection in our core-focused surveys? The absence of these stellar ghosts isn't just a bookkeeping error. It's a challenge to our understanding of how star clusters live and die. Every missing remnant forces us to reconsider the violence of stellar interactions, the quirks of star formation, and even the hidden architecture of gravity itself. Whether they've been flung into the void, swallowed by darkness, or simply overlooked, their vanishing act reminds us. In the universe's oldest neighborhoods, the dead don't always stay where you'd expect. Black holes are the ultimate cosmic ghosts, invisible, elusive, and packing enough gravitational punch to warp space itself. In the dense cores of star clusters, where stars jostle like rush-hour commuters, theory says these dark monsters should be everywhere. Massive stars live fast, die young, and leave behind black holes as their tombstones. Given enough time, a single cluster could produce dozens, even hundreds of them. Yet when astronomers scan these stellar metropolises, they find a puzzling shortage. It's as if someone took an eraser to the universe's ledger, scrubbing away half the black holes that should be there. Where did these missing monsters go? One possibility is a gravitational game of cosmic pinball. Imagine a black hole, fresh from the collapse of a massive star, drifting through the cluster's crowded core. With each close encounter, it gains speed, sometimes enough to fling itself entirely out of the cluster's grasp. Over billions of years, this relentless gravitational shuffle could eject black holes one by one, like a casino steadily draining a player's chips. Computer simulations support this idea, showing that dense environments can act like black hole catapults, hurling the heaviest residents into interstellar space. But here's the catch. Some clusters are so tightly bound, their gravity should trap even these dark fugitives, yet they're still missing. Then there's the hiding in plain sight theory. Black holes are, by nature, invisible unless they're actively feeding. A dormant black hole could lurk mere light years away, its presence betrayed only by the subtle wobble of nearby stars. Some clusters might host entire populations of these stealthy giants, their gravity subtly shaping stellar motions without a single X-ray flicker to give them away. A few tantalizing clues support this. Stars orbiting empty patches of space at breakneck speeds, or unexplained gaps in the cluster's core where something massive, but unseen, must be lurking. But the most electrifying idea: black holes might not play fair with our models. What if they're not solitary predators but pack hunters, merging into ever larger monsters over time? Picture two black holes locked in a slow dance, their orbits decaying until they collide in a universe-shaking burst of gravitational waves. The newborn black hole, now heavier, could receive a kick strong enough to eject it from the cluster entirely. Or it might sink deeper into the core, devouring its kin in a dark feast. Either way, the result is the same. Fewer black holes than predicted, their absence a silent testament to the violence simmering beneath the cluster's glittering surface. The implications ripple far beyond a single missing monster. If black holes are vanishing from clusters, where are they landing? Could these ejected wanderers be the seeds of the supermassive black holes that lurk in galactic centers? Or might they drift through the void as rogue nomads, invisible and untethered? Every undetected black hole forces us to rethink the life cycle of these dark giants, and the hidden mechanisms that shape the universe's most extreme environments. The truth might be stranger than we've dared to imagine. Deep in the cores of some star clusters, where thousands of stars jostle in a gravitational frenzy, there's an unexpected chill. A temperature drop so pronounced it's like stumbling upon an icy cavern in the middle of a desert. These stellar metropolises should be blazing furnaces, their densely packed stars colliding, heating gas, and radiating energy into the void. Yet when astronomers measure their thermal profiles, they find central regions far cooler than physics predicts, as if some cosmic air conditioner were silently siphoning away the heat. This isn't just a minor discrepancy. It's a full-blown thermal rebellion, a paradox that challenges our understanding of how energy flows in the universe's most crowded neighborhoods. The mystery starts with the basics of stellar thermodynamics. In a cluster's core, stars orbit at breakneck speeds, their gravitational interactions constantly stirring the pot. Collisions, near misses, and shockwaves from stellar winds should heat the sparse gas between stars to millions of degrees, creating a glowing, high-pressure environment. Yet in these anomalous clusters, the core gas hovers at unexpectedly tepid temperatures, sometimes cooler than the outskirts. It's as if the heart of a bustling city were somehow colder than its suburbs, defying all logic of urban heat islands. One leading suspect is a hidden population of cold gas clouds, lurking unseen in the cluster's core like cosmic ice cubes. These frigid pockets could absorb thermal energy, cooling their surroundings through molecular interactions. Picture a scorching summer day suddenly relieved by a hidden underground stream. The chill isn't obvious until you dig deeper. But here's the catch. Most clusters should have blown away such delicate clouds eons ago, their gas evaporated by relentless stellar radiation. If cold clouds persist, they'd need some invisible shield, some force field protecting them from the heat. That's where dark matter re-enters the scene. If these clusters are embedded in clumps of exotic, weakly interacting particles, their gravity might sculpt the gas into stable, cooling structures. Think of it as an invisible sponge, soaking up thermal energy and radiating it away in a form our telescopes can't detect. Yet even this elegant solution has holes. Some cold core clusters show no signs of the dark matter concentrations needed to explain the effect. The most tantalizing possibility, we're seeing a new form of energy transfer at work. Magnetic fields, twisted into complex geometries by the cluster's turbulent motions, might act like cosmic refrigerators, channeling heat outward along invisible lines of force. Or perhaps the gas itself is behaving in ways our models don't account for, with exotic quantum effects emerging at these extreme densities. A few theorists even speculate about vacuum energy, the same mysterious force driving the universe's expansion, acting locally to sap thermal energy from these regions. What makes the cold heart paradox so mesmerizing isn't just the temperature drop, it's the sheer audacity of its existence. These clusters are thumbing their noses at thermodynamics, daring us to rethink how energy moves through the cosmos. Whether it's hidden matter, unseen forces, or physics begging for revision, one thing's clear: the universe's cooling systems are far more mysterious than we ever imagined. And as we probe deeper into these icy cores, we're not just solving a puzzle, we're uncovering a whole new chapter in the story of cosmic thermodynamics. Star clusters are supposed to be cosmic snow globes, symmetrical shimmering spheres of stars held together by gravity's gentle grip. But hidden among these celestial orbs are bizarre outliers. Clusters stretched like taffy or squashed flat as pancakes, their contorted shapes defying the pull of gravity alone. These cosmic shapeshifters twist and bend in ways that rotation can't fully explain, as if invisible hands are kneading them like dough. What kind of forces could warp entire stellar cities into such unnatural forms? The first suspect is galactic tides, the gravitational tug-of-war between a cluster and its host galaxy. Picture the moon's pull stretching Earth's oceans into high and low tides. On a far grander scale, a galaxy's gravity might distort a cluster orbiting too close, elongating it like a comet's tail. Yet many of these misshapen clusters drift in quiet galactic suburbs, far from the disruptive forces of dense spiral arms or central black holes. Their deformations persist even where tides should be weak, suggesting another sculptor is at work. That's where magnetic fields enter the scene. Most clusters are thought to be too diffuse for magnetism to dominate over gravity, but recent observations reveal faint magnetic signatures threading through some distorted clusters like invisible wires. These fields, potentially remnants from the cluster's birth cloud, could act like cosmic puppet strings, guiding gas and stars into flattened disks or filamentary streams. Imagine sprinkling iron filings near a magnet. Their sudden alignment mirrors how stars might respond to these hidden forces. But not all shape-shifted clusters show magnetic traces, leaving gaps in the theory. The most puzzling cases are clusters with asymmetrical warps, one side bulging outward while the other remains pinched. These lopsided forms hint at violent pasts, collisions with dark matter, close encounters with rogue black holes, or even mergers with other clusters long ago. Like a car door dented by a forgotten impact, their twisted shapes could be cosmic fossils of ancient chaos. Computer simulations show such events can leave clusters permanently creased, their stars frozen in distorted orbits like a stunned crowd after an explosion. Yet some shapeshifters refuse to fit any mold. A few exhibit spiraling arms or hourglass waists, structures so intricate they resemble galaxies more than star clusters. Could these be hybrid objects caught in the act of evolving into something new? Or might they harbor dense cores of dark matter, their invisible mass twisting the surrounding stars into unexpected configurations? Every bizarre contour is a clue, a silent testament to forces we're only beginning to map. What makes these cosmic contortionists so mesmerizing isn't just their forms. It's what they reveal about the hidden pressures shaping the universe. Whether sculpted by tides, magnetism, or forgotten collisions, their very existence proves that even the simplest structures can become masterpieces of celestial chaos. And as we decode their distortions, we're not just solving a puzzle, we're reading the universe's diary, written in the bends and curves of starlight. Among the silent sea of stars in these ancient clusters, where radio emissions usually come from identifiable sources like pulsars or colliding gas, there's an eerie anomaly, faint, diffuse whispers crackling across the airwaves with no obvious origin. These aren't the sharp, rhythmic pulses of neutron stars or the roaring static of supernova remnants. These signals are softer, more elusive, like static from a radio tuned between stations, humming just loud enough to tease detection but never clear enough to decipher. And the strangest part, they seem to emanate from the empty spaces between the stars as if the void itself were singing. One leading explanation sends chills down the spines of astrophysicists: dark matter annihilation. If dark matter particles, whatever they are, collide and annihilate in the dense hearts of these clusters, they could release energy as faint radio waves. Picture a vast, invisible bonfire burning in the spaces between stars, its heat so subtle we only catch the faintest glow. Some models suggest certain types of dark matter, like WIMPs, weakly interacting massive particles, could produce just such a signal when they interact. The cluster's strong gravitational fields would concentrate these particles, making annihilation more likely. But here's the catch. Not all whispering clusters line up with predicted dark matter hotspots, and the signal's uniformity lacks the telltale most dark matter theories expect. Then there's the plasma paradox. Could ultra-hot, ultra-thin gas, ionized to the point of becoming a soup of free electrons and protons, be generating these whispers? In most of space, such plasma emits X-rays, not radio waves. But under extreme magnetic fields, like those possibly tangled through these clusters, charged particles could spiral along invisible lines, synchrotron radiation twisting into the radio spectrum. It's like a cosmic neon sign, flickering in frequencies we're only beginning to decode. Yet even this explanation falters when faced with the signal's peculiar stability. Plasma turbulence should crackle and fade, but these whispers persist, unwavering, as if powered by something far more deliberate. The most tantalizing possibility: we're hearing the echoes of exotic physics, phenomena outside the standard model. Axions, hypothetical particles theorized to solve quantum puzzles, could convert into radio waves in the presence of strong magnetic fields. Or perhaps primordial black holes, smaller than an atom but as heavy as mountains, are evaporating via Hawking radiation, their death throes ringing out as static across the cosmos. A few daring theorists even speculate about cosmic strings, defects in spacetime left over from the Big Bang, vibrating like guitar strings and broadcasting their oscillations into the void. What makes these radio whispers so haunting isn't just their mystery, it's their persistence. They don't shout, they murmur, patient and omnipresent, as if carrying a message we're not yet equipped to understand. Whether they're the fingerprints of dark matter, the hum of unseen plasma, or the static of new physics, one thing's certain: the universe is still speaking in riddles, and these clusters are its most enigmatic transmitters. Every faint signal is a breadcrumb, leading us deeper into the cosmic unknown. Gravity is supposed to be the universe's steady hand, a force so reliable we base our cosmic maps on its predictable pull. But deep within certain star clusters, something peculiar stirs. Sensitive instruments have picked up faint tremors in the fabric of spacetime itself, subtle gravitational ripples that flicker through these stellar communities like phantom footsteps. The strangest part: there's no visible source. No hidden black holes, no dense knots of stars, not even the usual suspects like neutron stars or rogue planets. Just empty space, pulsing. These tremors aren't the violent spacetime waves produced by colliding black holes. They're far quieter, more like the hum of a distant engine, a rhythmic distortion that tugs stars ever so slightly off course. Imagine floating in a calm lake when suddenly, without a splash or ripple, you feel an unseen current brush past you. That's the kind of eerie precision astronomers are dealing with. Some clusters seem to harbor invisible disturbances, their gravity flickering as if something massive is moving through them. Unseen. One explanation points to dark matter in motion. If these clusters are threaded with dense clumps of the universe's most elusive substance, their gravitational shadows could warp spacetime briefly as they drift. Picture a school of fish swimming beneath a boat. Their presence distorts the water's surface even if you never see the fish themselves. But here's the catch: dark matter is supposed to be smoothly distributed on small scales, not clumped tightly enough to create these ripples. Unless, of course, we've misunderstood its behavior entirely. Could dark matter form microscopic knots or fleeting structures, like cosmic eddies in an invisible river? Then there's the spacetime wrinkle theory. Taught us that massive objects bend the fabric of the universe, but what if that fabric isn't perfectly smooth? Like a crumpled sheet left with permanent creases, the universe might retain subtle folds from its earliest moments, primordial wrinkles frozen into the cosmos during the Big Bang. As star clusters glide through these warped regions, their gravity meters might register faint tremors, the cosmic equivalent of a ship rocking on hidden swells. But the most electrifying possibility: these ripples could be echoes of something even stranger, quantum fluctuations scaled up to cosmic proportions. On the tiniest scales, particles blink in and out of existence, creating a frothy, unstable vacuum. What if, under extreme gravitational conditions, that quantum turbulence leaves faint fingerprints on spacetime itself? It's a radical idea, but one that could explain why these tremors appear and vanish without warning, like whispers from a dimension we're only beginning to sense. What makes these gravity ripples so mesmerizing isn't just their mystery, it's their audacity. They're cosmic breadcrumbs hinting at forces or phenomena we've yet to name. Whether they're dark matter's shadow dance, spacetime's hidden topography, or something beyond our current physics, one thing's clear. The universe is still humming secrets, and star clusters are its most enigmatic tuning forks. In the orderly orbits of star clusters, where gravity keeps most stars moving at steady, predictable speeds, a few rogue stars break all the rules, suddenly kicking into overdrive as if pushed by unseen hands. These phantom accelerations aren't gradual, they're sharp, unexpected bursts of speed, like a car lurching forward without the driver touching the gas. The strangest part. There's no visible culprit, no nearby black hole, no dense knot of dark matter, not even a close encounter with another star to explain the sudden boost. So what cosmic prankster is flinging these stars into overdrive? One clue lies in the timing. Some of these speed boosts happen in otherwise quiet regions of clusters, far from the gravitational turmoil of the core. It's as if the stars brush against something invisible, a gravitational bump in the road that sends them rocketing forward. One theory suggests these could be flybys from compact dark objects, rogue planets, neutron stars, or even primordial black holes too small to detect directly. Picture a star sailing through space, passing near a hidden black hole no larger than a city. The hole's gravity would tug the star sharply, imparting a burst of speed before vanishing back into the darkness, leaving no trace except a suddenly faster-moving star. Then there's the slingshot effect, but not the kind we're used to. Normally, stars gain speed by swinging around massive objects like black holes or binary systems. But some accelerated stars show no signs of such encounters. Instead, their trajectories suggest they've been grazed by something far stranger, topological defects in spacetime itself. These hypothetical structures, relics of the early universe, could act like cosmic trampolines, warping space just enough to give passing stars an unexplained kick. Imagine running your hand across a tablecloth riddled with tiny wrinkles. Your fingers might catch on imperfections you can't see. Stars could be experiencing something similar, their paths jolted by invisible folds in the fabric of reality. The most perplexing cases are stars that accelerate repeatedly, as if whatever's nudging them is stuck in their orbit. This isn't a one-time gravitational handshake, it's an ongoing push, like a metronome ticking in the void. Could these stars be trapped in the gravitational web of a hidden object, something massive enough to tug on them rhythmically but faint enough to evade detection? Or might they be threading through a dense field of dark matter particles, their cumulative collisions adding up to a steady acceleration? The math leans toward the former, but the universe has a habit of surprising us. What makes these phantom accelerators so thrilling isn't just the mystery, it's the sheer audacity of their defiance. Every unexplained speed boost is a challenge, a dare from the cosmos to look beyond the visible and consider the invisible architectures shaping our universe. Whether it's dark objects, spacetime quirks, or something entirely unnamed, one thing's clear. The star clusters we thought we knew are still hiding players in the shadows, and they're just starting to show their hands. This theory of general relativity paints a clear picture. Massive objects warp spacetime, slowing time itself in their gravitational grip. Near a dense star cluster's heaviest members, atomic clocks should tick noticeably slower than those farther out, like a cosmic version of a clock running late in a deep valley. Yet when astronomers measure these time dilation effects in some extreme clusters, the numbers don't add up. The slowdown isn't as pronounced as it should be, as if the universe's stopwatch is ignoring its own rules. It's not just a minor discrepancy, it's a full-blown rebellion against one of physics' most sacred principles. Take the case of a cluster hosting a neutron star binary, where one ultra-compact object whips around its companion at blistering speeds. According to relativity, the intense gravity and velocity should stretch time like taffy, delaying signals from the inner orbit by microseconds compared to the cluster's outskirts. Yet observations reveal delays smaller than predicted, sometimes by a factor of 2 or more. It's as if someone reached into the fabric of spacetime and dialed back the warping effect, leaving scientists scrambling to explain why. One possibility cuts to the heart of modern physics. Möbius equations, while stunningly accurate in most cases, need tweaking under extreme conditions. Imagine gravity as a rubber sheet that stiffens slightly when stretched too far, its warping effect lessening under pressures we've yet to encounter on Earth. Modified gravity theories, like MOND's more radical cousins, suggest subtle adjustments could resolve the mismatch without invoking unseen matter. But here's the catch: these tweaks often break other relativistic predictions, like the precise orbital decay of binary pulsars. If gravity's rules change here, why not everywhere? Then there's the measurement problem. Time dilation isn't something you can observe directly. It's inferred from starlights or the delayed pulses of orbiting neutron stars. Could interstellar gas clouds or magnetic fields be distorting these signals, masking the true extent of time's slowdown? Picture trying to measure a shadow through frosted glass. The blur might make the shadow appear fainter than it really is. Some clusters do harbor turbulent plasma that could scatter light, but not enough to account for the glaring discrepancies in the most extreme cases. The wildest explanation: these clusters might be threaded with exotic matter, particles that counteract gravity's time-warping effects. Certain quantum fields, if concentrated enough, could theoretically stiffen spacetime locally, making it more resistant to bending. It's like pouring syrup into water. The mixture becomes thicker, changing how waves move through it. If such fields cluster around massive stars, they might subtly shield the surrounding space from full-time dilation, creating pockets where relativity's grip feels oddly weak. What makes these cosmic clock anomalies so electrifying isn't just the challenge it's the sheer audacity of their existence. Every mismatched measurement forces us to confront the limits of our understanding. Whether it's new physics, hidden forces, or observational blind spots, one thing's clear: time itself may not be as obedient as we thought, and these clusters are where its rebellion shines. At the smallest scales of the universe, particles flicker in and out of existence, entangled in a delicate quantum dance where reality itself seems uncertain. Now imagine that same unpredictability, those same bizarre rules, playing out among entire star clusters, where the motions of billions of stars might hinge on the same physics that govern atoms. This is the radical idea at the heart of the quantum cosmic connection: that the strange behaviors we see in clusters, phantom accelerations, missing mass, even those eerie radio whispers, could be shadows of quantum mechanics writ large across the cosmos. The first clues come from entanglement, that spooky quantum phenomenon where particles remain mysteriously linked across vast distances. Change one, and its partner responds instantly, no matter how far apart they are. Now stretch that idea to a star cluster, where stars might exhibit synchronized motions that classical physics can't explain. Picture two stars on opposite sides of a cluster, their orbits subtly mirroring each other in ways that defy gravitational models. Could some form of macroscopic entanglement be at work, weaving invisible threads between them? A few bold theorists argue that under extreme conditions, like the mind-bending densities near a cluster's core, quantum effects might scale up, imprinting their peculiar logic onto stellar dynamics. Then there's the uncertainty principle, which says we can't perfectly know both a particle's position and momentum at once. Apply that to star clusters, and suddenly their gravitational mismatches take on new meaning. If the very fabric of spacetime has a quantum fuzziness at galactic scales, it might explain why we can't pin down the exact mass distribution in these systems. Not because our instruments are flawed, but because the universe itself refuses to be fully measured. Some clusters exhibit gravitational lensing patterns that flicker unpredictably, as if the mass warping the light is somehow smeared across probabilities rather than fixed in place. The most tantalizing possibility involves vacuum energy, the seething quantum foam that fills empty space. On Earth, its effects are vanishingly small, but in a star cluster's crowded core, where gravity and density reach extremes, could this energy bubble up into the macroscopic world? Imagine it acting like an invisible pressure, subtly nudging stars apart or stabilizing orbits in ways that mimic dark matter's effects. It's like blowing on a house of cards to keep it from collapsing. Except here, the breath comes from the universe's own quantum foundations. Skeptics, of course, point out the staggering leap required to bridge quantum mechanics and celestial mechanics. The scales are so vastly different that invoking quantum phenomena seems absurd, like using a microscope to study a mountain. Yet the anomalies persist, piling up in ways that defy classical explanations. Perhaps the answer lies not in choosing between quantum or gravitational models, but in something entirely new, a theory that unifies both, revealing a cosmos far stranger and more interconnected than we've dared to imagine. What makes this quantum connection so electrifying isn't just the science, it's the philosophy. If true, it would mean the universe operates not as separate realms, big here, small there, but as a single, seamless tapestry where the rules of the infinitesimal whisper to the motions of the cosmic. Every odd cluster behavior could be a clue, a fingerprint left behind by physics we're only beginning to glimpse. And as we peer deeper into these stellar enigmas, we might just find that the key to understanding the universe's largest structures has been hiding in its smallest details all along. Among the countless mysteries of star clusters, none pushes the boundaries of science and philosophy quite like the consciousness controversy. It's an idea so radical it borders on science fiction. What if the very act of observation, the presence of a conscious mind, somehow influences the behavior of these cosmic structures? At first glance, it sounds like fantasy, but this notion taps into one of quantum physics' most bewildering principles, the observer effect, where particles behave differently when measured. Could this quantum quirk scale up to galactic proportions, subtly shaping the anomalies we've been puzzling over? The roots of this theory stretch back to the double-slit experiment, where particles act as waves until observed, then abruptly choose a definite state. In the quantum realm, reality seems to dance to the tune of measurement. Now imagine applying that logic to star clusters. What if their gravitational oddities, missing mass, phantom accelerations, even those eerie radio whispers, aren't just puzzles to solve, but reflections of our own interaction with them? It's like stepping into a cosmic hall of mirrors, where the act of looking changes what's reflected. Skeptics, of course, dismiss this as metaphysical speculation. After all, quantum effects typically vanish at macroscopic scales, drowned out by the noise of countless particles. But here, where star clusters throw a wrench in conventional thinking, these systems, though vast, operate under extreme conditions, ultra-dense cores, chaotic gravitational interactions, and environments where quantum phenomena like entanglement might persist longer than expected. Could clusters exist in a peculiar middle ground, where quantum rules don't entirely fade? The implications are dizzying. If consciousness plays a role, even indirectly, it would mean the universe isn't just a cold, mechanical clockwork. It's a participatory arena where observation and reality intertwine. Some theorists suggest that advanced civilizations, by merely studying clusters, might leave gravitational footprints in the data. Others propose that dark matter itself could be sensitive to quantum measurement, its distribution shifting in response to how closely we look. But the most provocative idea, that star clusters in their own unfathomable way might be alive in a quantum sense. They're anomalies, not errors in our models, but evidence of a deeper mind-matter connection woven into the fabric of spacetime. Whether this theory holds water or not, it forces us to confront an exhilarating possibility that the cosmos is far stranger, far more interactive than we ever dared to dream. And in that uncertainty lies the most thrilling mystery.